maybe we can have Lijun and Ethan to introduce yourself.
Hi everyone, I'm Li Junyu. I'm currently a graduating PhD student from Carnegie Mellon University. I have also worked at Google as a student researcher for quite a few years. For the past 2 years, we work on video generation. From early on, I worked on transformer-based video generations, which led to the latest release called VideoPoet. It's a large language model style model of multimodal video generation.
My name is Ethan. I work on LLM and generative AI training framework at NVIDIA. We have two open source library called Megatron and Nemo on GitHub. So you can train the LLMs on very large scale, like trillions of parameters. And we also release some open source model training recipes like Llama, Mixtral. Previously, I worked at Facebook AI Research on large scale self-supervised learning. I graduated from Carnegie Mellon.
Also, I just started a YouTube channel. Welcome to subscribe me. I was wondering from a technical perspective, what techniques or data or something that makes it so powerful?
I was expecting something similar to come by the end of 2024, but it actually came at the beginning, which was a very fast forward, and many people are trying to reproduce it because now it's verified. Sora uses diffusion transformer in the latent space. So we know how to build latent spaces with discrete or continuous tokenizers. We also know how to train diffusion transformers for images and later for videos. They really scale this thing up to say in the sequence length and tens of thousands of GPUs and hundreds of millions of data.
I think my biggest impression is that scaling law on vision is proved. If you have a self-supervised learning pre-training model like mass encoder, even if you scale it to like 100 times, it's not going to change how it affects the world. It's just gonna be another model with a better performance on some of the benchmark. Stable diffusion, it becomes larger and larger, but it's just a visual effect. It becomes slightly better, bit by bit. Everybody is hitting the ceiling, but now we are seeing a scaling law that we can add more data and scale the model, the infra to get a better model, better intelligence.
Do you think they will switch to DIT as well?
DIT stands for diffusion transformer. It uses the standard transformer architecture with bidirectional attention. It's trained with the diffusion objective by doing denoising step by step. So nowadays, we've seen autoregressive transformers are very scalable, proved by the LLMs. And this time, diffusion transformer is also scalable. Going back to the frameworks of various products and open source projects, Stable Diffusion 3 is definitely a diffusion transformer-based model. The other companies like Runway, Pika, Sora, AnimateDiff, they are latent diffusion models, which means we do not do the diffusion denoising process in the pixel space. Those pixel diffusion models can be viewed as the first generation of models, like starting from DDPM, later on Imagine Video. Now the models we talk about are all latent diffusion models, which means we first use variational autoencoder or other similar frameworks to downsample the videos, pixels, images into a low-dimensional manifold so that the processing speed is much faster. After we downsample, we do the diffusion denoising training in this latent space. Usually, people have been using the U-Net architecture for long, which became popular from the first version of Stable Diffusion until the latest release of their third version. Similarly, all those video model companies have been using U-Net-based architectures probably until now. But I believe after seeing Sora, everybody is shifting towards the diffusion transformer, which is much more scalable. But this one may be more costly when you achieve really high quality.
I can talk about U-Net versus diffusion transformer. U-Net excels in training stability and convergence. It's easier to train than DIT. That's probably one of the reasons why it was prevailing before OpenAI released Sora. Because U-Net have this kind of long skip connections, it connects the embeddings from the beginning to the end. High resolution features are going through skip connection to the end, and also low-level features also go to some layers way behind them. They can easily learn the image features. You're trying to approximate image from image. This kind of skip connections would help that. Diffusion transformer, it does not have this kind of inductive bias, so it's harder to train this model. It's kind of similar to vision transformer versus convolution neural network. Convolution neural networks, they have an inductive bias of locality, but vision transformer is just global attention. It's going to learn this kind of locality through training, so it's much harder to train. In the development of our Megatron repository, we have pipeline parallelism where you slice the models into multiple stages. You can actually put multiple stages on different devices. You can scale the model size almost infinitely. On the other hand, it's autoregressive versus diffusion. Autoregressive is usually used in transformer and language modeling. It performs very well in language domain. But actually, diffusion can also be used for language modeling. I remember there's a previous talk from Ilya Sutskever from OpenAI. Ilya mentioned autoregressive is naturally better than diffusion and mass language modeling because autoregressive is lacks token prediction, which is conditional probability. So you're trying to predict the future based on the past. However, the mass language modeling like BERT is going to mask out some of the tokens and leave out some of the tokens in the middle. And diffusion is going to construct some of the steps out of nowhere. So they have some kind of synthetic middle steps where it doesn't exist in the nature. That's part of the reason autoregressive is stronger than diffusion and BERT. OpenAI also tried ImageGPT, which is autoregressive for generating image and videos. Ultimately, once you have enough compute, you don't have to use diffusion. You can just generate stuff in one step. But currently, compute is limited. Diffusion is still better. You kind of compressed a larger model into multiple diffusion steps. So it's kind of like a model like 50 times or 100 times larger than the original model.
We are also interested in some of the limitations of Sora, why this may happen. How long you think it will be improved in the future?
This can come from two aspects of errors. One aspect is the data, the other aspect is the model. So on the data side, first of all, we are not clear what data Sora used in the training. It's probably true that a part of the data, it is real, like surveillance cameras, robotic, self-driving car recordings. Those are real, but there are also other things like people post on YouTube, TikTok, and other platforms, or even from the TV shows and movies. There are special effects. Those contents naturally do not follow the physical rules. If the model is trained to produce these things, then the content we see, they will not. Maybe we need to either filter out data that only follows the physical rule or label these data, whether it is or not. On the modeling side, it's ultimately just the accuracy of the model prediction. It's just like the hallucination of large language models. In the early days, we can do machine translation. Later, we may be able to write novels from short to long with language models. We don't really care if it's real or not. But nowadays, we can use LLMs to do reasoning, to write code, to solve math problems. This is when we require them to follow all the rules we define. And for videos, we see maybe Sora is like the GPT-2 level of model. Earlier, the other models would be just doing machine translation. Now it's a little more advanced, but still it's far from accurate to precisely mimic the real world. And that's why in many samples, we will see it breaks the physical law, or it makes a person having 6 or 4 fingers and with 4 feet. It's fine for entertainment, but not fine for robotics or embodied interaction. The speed to achieve that depends on a couple of factors, like how much data we can end up collecting and how accurate we can label whether this is real or not, and also how much compute we can provide or use, and how much improvement each generation of GPUs is bringing along us.
Yeah, if you look at the improvement on especially fingers and faces on Stable Diffusion, it's improved within about a year from like generating imperfect fingers to perfect fingers. Currently, those images I cannot even identify if they're real or not. So initially, you can look at some imperfections in the human body. But now I realize I need to look away from the main object in the image. I have to look at in the background, for example, if the stop signs make sense in the background. I guess in the near future, within a year, these kind of inconsistency problem should be solved really fast. I think it's primarily a data problem. For example, to solve finger problem, you need to collect a lot of this kind of data and balance them during training or even just fine-tuning. On the other hand, once the model capability improved to another level, a lot of these kind of problem will automatically disappear.
OpenAI CTO recently accepted an interview. She says the
publicly
training
available,
data is all available,
yeah,
and
publicly available
license
to
data,
use.
including Shutterstock.
There might be
And that she's
the data,
not sure
but
about whether
I'm not
use
sure. I'm
videos
not
on
confident
YouTube.
about it.
The CTO, she didn't answer the question about the data. But YouTube have clear policy. Their data cannot be used for machine learning. It's unclear whether they use it or not. They already admitted they use Shutterstock. High quality data is very common for large scale training. For example, in GPT training, they have a small data set of high quality data like from book and Wikipedia. And then they will train a classifier to classify whether a piece of text is good quality or not. For video, they will probably do the same. For gaming engine, I'm not exactly sure about that because OpenAI have a very small team. On YouTube, there are already a lot of games videos. I guess except that the difference is once you want to apply the model to, for example, robotics, it would be helpful to have this kind of engine.
What kind of training data is good quality?
Right now, there are actually two paths. Maybe they will converge in the end, but right now we can optimize for the visual appearance or optimize for the physical rules word model. Say we have self-driving recordings. Models trained on those data will have really good senses of the real world. But if you use it for text to video, it would be really boring. On the other hand, if we have a lot of videos like from movies, TV shows, fun stuff from media people posted, and we properly label it with the captions in rich text, we can use that to train a model for entertainment purposes or for video creation and editing purposes very well. For entertainment, usually we care about high aesthetic data, meaning that the style, the appearance, and the movement. Usually people can use some filters. Even you can hire artists to design filters for you, like, oh, this is the type of video certain group of people usually create. These high quality data actually lack large language models because they are not in an abundant amount. They can be used in a fine-tuning stage. My personal opinion, including when we developed VideoPoint, was that you can just throw in whatever data you have to make the model learn general knowledge about the video domain and the connection with the other modalities like audio, image, and text.
Human feedback loop. Like, how much do you think this will help?
I think this will quickly become one of the biggest mode. It's going to align with the user's aesthetic. Collecting this kind of data is extremely expensive if you're going to label it yourself. But with user interaction, they can get this kind of data for free. And ChatGPT, they already generate like trillions of tokens every day. Currently, they're not utilizing this data very well, but in the future, it will be extremely important and it's harder for other company to catch up.
This is a very important methodology to use in the development of video models, and it's actually very underexplored. If somebody is going to do video generation products like text to video, they can collect these human feedback, just spinning up the data flywheel. And it's actually depending on what groups of user you would have. They would have different preferences.
Yeah, I think it's even possible for them to customize to each of the user. Currently, they have the memory function for GPT. It customize your experience.
I agree. And if we take one step further, we may say we have really precise profiles for each user, and then we just generate videos based on their profile. This could replace the recommendation systems of social media entirely.
during OpenAI Sora's training, a lot of its infrastructure came to play an important role. For startups who don't have these very good infrastructure, what are some solutions, alternatives?
A lot of requirements on infrastructure nowadays to rebuild something like Sora. As you mentioned, we need a couple models to prepare the data. Even before that, we need a really scalable pre-processing pipeline to say download, decode, and filter all these video files because they will be very huge. It's adding one more dimension to images is the most expensive modality you can have right now. That means you are going to be dealing with like petabytes of data if you really have a lot of them. And then you need models to label these data and also select them. Usually, large language models, there are a couple of variants that you can use for open source. Maybe you use Llama or Mistral. Maybe you use it for prompt rewriting. For captioning, you need some model that understand the visual aspects. If you are rich, you can just call APIs, right? Pay for it. And then when you train it, I think that is the most challenging part for infrastructure because you want to train with tens of thousands of GPUs. So you will have to do like sequence parallel among other types of parallel to train it efficiently. And there's going to be a lot of challenges. And also recently people have been complaining about the reliability of GPUs. You may only discover it after a couple hours, the job has been running. And when a single chip goes down, the entire job may fail if you do not handle it properly. You may need smart ways to reroute the compute for this chip to some other chips, or you just get rid of this machine and switch to some other machines.
Yeah. And Lichun also mentioned the sequence parallel because people have speculated Sora used like millions of tokens for context lens. We actually already have the solutions in Megatron. We have what we call sequence parallel and context parallel. So context parallel, it would slice the attentions into multiple devices, kind of like how flash attention works.
How big the Sora model is, the inference time generating a 1 minute video.
Maybe we can first go with inference time, since I think OpenAI people have also commented on that. It's like a couple minutes, maybe up to 10 minutes, which is better than we originally expected, I'd say, for myself. But on the other hand, maybe it's using a lot of GPUs in parallel with 100 GPUs. And about the model, my personal opinion is that it's below 10 billion parameters because they haven't really proved that it can scale to hundreds of billions. And even at the 10 billion scale, handling the 1 million sequence length is already a very big challenge for the hardware. It's bigger than original people estimate on social media, say maybe 3 billion. I think the estimate would be, let's say, between 7 and 10 billion.
Even though it's a small model, it has very large context lens, which make it not that small. I guess previous OpenAI talks, I found that usually they would fit a model that you can physically fit into the machines. They would choose like model hidden dimensions up to the point where the memory is full. So I guess they would use the full capability of their clusters. It's definitely gonna be millions of context lens and tens of billion parameters.
You think Sora could be classified as a world model? And what's your own definition of the world model?
Disagreement from Yann LeCun was primarily whether it should have a decoder. He believes that you do not build a world model with decoder because there are millions or even billions of possible outcomes for the next timestamp in a word. Basically, you cannot predict what's going to happen in the future. If you have a decoder to predict what's going to happen next, it's going to fail miserably. He instead proposed JAPA, which is trend embedding predictive. Instead of doing a decoder, it's going to use an encoder to encode the state of the world. And they're going to do the prediction in the hidden states. This will avoid the millions of possibility in the outcome. In the hidden states, it's no longer a one-to-one mapping. One hidden state can map to multiple outcomes, multiple decoded results. The model can better learn the world states. That's his argument. I don't think it's necessary to discard the decoder. Sora already demonstrated a very good generation result.
So first of all, I think Sora is a big step toward a world model, but it's not it yet. There are two reasons. One is, as we have discussed a lot for, it does not follow the physical rules very well. And one more important reason is it does not allow action as inputs, so that you cannot interact and control the future outcome in a, say, autoregressive manner for infinite long video generation. And I think that's a critical property for world model to be useful. Going back to the discussion with Yann LeCun's JEPA architecture, I actually like some of his design and let's say half of his arguments. First of all, I can agree with him that the probabilistic models may not be very good when used as word models. Because when we are trying to learn that probability distribution, there's very high chance that we go in the correct way, following all the physical rules. But there are always chances that when you do the sampling process, you select some rare cases that it breaks the law. You can never prevent these things from happening. Although in the language modeling space, it's less an issue, and especially when you just say in text, when you make a typo, it's okay. But for word model, if you want it to simulate physics, I don't think that's the ideal case to use. But I also don't like JEPA, because I think you should go back to pixel space. Richard Feynman said that what you cannot create, you do not understand. You should be able to create those pixels. There are a lot of entropy or uncertainty when you want to create every pixel, or maybe you discard the pixel representation, you just create all the particles in the world. There are a lot of uncertainty given the things you observe. Even for video prediction problems, you cannot really accurately predict how the tree waves will move because you don't know the wind. But if you have enough input, you can definitely precisely predict that. JEPA uses a latent variable, say this is the random noise as input. We use that to predict embedding of the other space. To my opinion, maybe you can just use that to predict the pixel space output or the real space output of another modality, so long as you capture all the latent, unseen, unknown dependencies in those latent variables instead of the sampling procedure.
Do you think to achieve the world model, we should adopt a end-to-end strategy, maybe with the help of physical engines?
I think we should not use a physical engine when we build a world model. The ultimate super intelligence style of world model, we wanted to discover new physical rules to help understand the universe, so that it is super intelligence, it's smarter than all of us. Maybe it discovers another law of relativity. To do that, we should not constrain it with all the physical priors we already have. Maybe as a first step of verification, we should be able to do something that rediscover all the laws we already have, like Newton's laws in the low speed scenario. So I believe a pure data-driven setup. Sora itself is also not an end-to-end model because it has the encoders and decoders for pixel to latent to pixel. And it also has the text encoders, also even the prompt rewriting engine with GPT. So it has many modules.
Do you think computer vision will be solved by a model like Sora, or maybe its future version?
Computer vision is already kind of solved by some as a standard. It's able to maintain the 3D consistency, which means that the model can encode the 3D object in its hidden dimension. It also has the consistency across time, which kind of means it's also able to solve tracking. That's why it can keep every object consistent across different frames. I think most of the task in probably like 3 years by the same architecture in this line.
Text to video generation is definitely going to have a lot of implications to other fields as well.
I think it's going to be a big boost for robotics and even self-driving. Action planner can be based on this generated content, or even the model that plans the action is just the same model that predicts the future. Because it understands it so well, it can choose the best action to proceed. That enables a lot of capabilities helping us in the daily life.
Some of the companies already been doing visual language action model, like Gaia from Vane, which is a UK autonomous driving company. They use large language model to do both understanding and planning. They would get the video language pair and ask the model how it should act based on the video. So the model is explainable. It can actually tell why it's going to this route, and it can also do the actions on top of the video.